So the confusing contention from here. So we've come over from here and said, all right, well, so G is a finite group, and so that means that every element has finite order.
Yeah,
That's a classic theorem.
And
from
this is, well, if you want to take
algebra.
a look more into this,
Mm-hmm.
well, this was the more general exercise in comparison to A1.
Uh-huh.
Just if we're looking at G being of finite order.
Okay. So then here's what happens with this logic going on here. So, as you say, applying the representation pi to both sides of this equation. We get on the left-hand side the nth power of pi of g, and on the right-hand side we get pi of e, and because e is the identity element, it gets represented by the identity matrix. So now, what does this step here mean?
Well, of course, there's unpackaging the minimal polynomial
of a
pi
matrix.
of g, which is this Cayley-Hamilton theorem. That's what that'll help.
Right.
us
So
with.
here's what happens: is we're going to take both sides we're going to subtract the identity matrix from both sides of this, and let me clear out some space so that we can do some writing. So subtracting the identity matrix from both sides. If we call pi of g, let's give it an easier name. Let's call pi of g a or something.
So that's kind of looking more polynomial-ish.
Right. So we have then a to the power n minus the identity matrix is equal to the zero matrix.
Okay.
Right, subtracting on both sides. And so what we've found is we've found a polynomial equation that the matrix A satisfies. Satisfied by A. Now, that means...
So like this, there would be maybe like a matrix T0 and T. T to the n. So T to the n plus...
Yeah.
Or just
let's just write it that way. That this polynomial equation,
would be like 1, and then T to the 0, I meant.
x to the n minus identity matrix equals 0. It is a polynomial equation satisfied by A.
This would be the 0th term.
And that would be, well, these are all matrices. Right.
Yes.
I and x and 0.
But I mean, we can still take powers of them.
We can take powers of a matrix, yeah.
Yeah. So
square matrix.
If we were to take the 0th power of a matrix, we get the identity.
Yes.
Yeah,
Yep,
so that's
yep,
what I'm talking about there.
Uh-huh.
Okay, and then this we substitute in for x a. That's the solution.
Right. So he's saying here that this is a polynomial equation satisfied by A, but on the other hand, depending on what value n takes, this polynomial might not be an irreducible polynomial.
Okay.
So now we're thinking, polynomial ring style. So we might be able to factor it. In particular, let's suppose that, well, let's just say n was 2 for a minute. So let's just suppose that we're representing, the finite group of order 2. Not a very interesting example, but it might help to pick apart what he's saying.
So if we were to have a matrix whose, a diagonal matrix, I mean, well, that's kind of, I think, would be most ideal here, diagonal matrix where the elements along the diagonal are plus or minus 1.
That's what would happen in this case, because this polynomial equation would factor. Factoring is a little more dicey in these equations because we have matrices, and matrices don't commute. Their multiplication doesn't commute. But we can still, in this case, at least factor. And so we find out that A...
yeah, because we don't know the cross result cancel.
Right, right. But in this case they do because we have, the only factors here are the identity matrix. Like one of the factors is always the identity matrix. And that does commute with everything.
Yeah.
So we can factor this. And this implies then that our matrix A either is the identity matrix, or it is the opposite of the identity matrix. So in this case, it's pretty easy to say what matrices we're going to have in our two-dimensional representation of the finite group of order 2. Right? It's either going to be the identity matrix or the opposite of the identity matrix. And the minimal polynomial of the whatever matrix we're talking about is going to be one of these factors or the other. Right? If A is the identity matrix, then here's its minimal polynomial. If A is not the identity matrix, then here's its minimal polynomial.
Okay.
So, of course, fun things happen when we crank up the power a little bit. Because as we got at least a little bit of an appreciation for in Abstract 2, maybe not as much as we could have, but some, that the cyclotomic polynomial,
Yeah,
x to the n minus
I don't think I was ever in this group.
x to the n minus 1, we can always factor it, at least a little bit, right? It's never irreducible. So, for example, if I'm going up to degree 5, let's say, then I can factor this into, I can always factor an a minus 1 out.
Oh, yes, I remember this. And
then the rest turns out to be a to the 4th plus a to the 3rd plus a
yeah,
squared.
I remember this. Okay, this is...
Plus a plus 1.
So this would be a cyclotomic polynomial?
Yes.
One that can factor into something like this where we just have a 1 degree term, or 1 degree polynomial, and then we have, for our other factor,
right,
the n minus 1.
So what are our options for this matrix A? Well, the matrix A could be the identity matrix, in which case its minimal polynomial would be that factor. But if A is not the identity matrix, in other words, we would here be representing the cyclic group Z mod 5 or something like that, right? That if it's not the identity matrix, that its minimal polynomial would have to be this thing, this degree 4, which happens to be irreducible polynomial.
But as long as it's a cyclotomic polynomial, we know that it'll be one of those.
It'll be one of these two, and it turns out that this factor is irreducible when we started with a to the 5th minus identity. And again, the reason we can get away with factoring this so easily, even though matrices don't commute in general, is that all the matrices that are participating in these factorizations are either A or I, and powers of A commute with each other, and everything commutes with I. So there's no problem in factoring this just like it's an ordinary polynomial.
But we know that we can always factor this cyclotomic polynomial.
At least a little bit. How much we can factor
a minimal polynomial.
Right.
And then just a minus I.
How much we can factor it depends on whether, it depends on the primality of this n. So we can always take out a factor of a minus I and do what we did here. The question is whether the remainder here is irreducible or not. And if n is prime, the answer is yes. So for the a to the 5th minus identity, this was irreducible. But, I keep forgetting I can't erase like I like to erase here. I've got to do this. But let's say I had, a to the 4th minus I. If n equals 4, then what I would have in my other factor would be a cubed plus a squared plus a plus I. And it turns out that that's not irreducible. It turns out that that factors into something like a plus I times a squared plus I, or something like that. Yeah, I think that's right. So that if we were decomposing an element of order 4, here, finding representations of an element of order 4, then its minimal polynomial would either be a minus I, a plus I, or a squared plus I.
Oh, okay.
So whatever its minimal polynomial is, it's going to be a factor of the polynomial x to the n minus 1.
Okay.
But how big that factor is, what its degree is, depends on a lot of things. Right? It depends on the order of the element, n, and the primality of that order. Depends on how much it factors. And it's not as closely related to the Cayley-Hamilton theorem as I thought, but what the Cayley-Hamilton theorem says is that there is always, for a square matrix, there's always some polynomial equation that the matrix satisfies. Namely, it satisfies its own characteristic polynomial. So every square matrix A satisfies its own characteristic equation. In other words, the equation you solve to get the eigenvalues?
Yes. If we were to put in the matrix A instead,
you would still get the zero matrix out of it. Which is kind of a neat theorem. Because we don't often plug matrices into polynomials, but it turns out that we can always find a polynomial equation of degree equal to n, if A is an n by n matrix, that matrix satisfies. Namely, the characteristic equation. And this is kind of like that, but not quite related, because we're not starting with the characteristic equation. Instead, we're starting already with a polynomial equation that the matrix satisfies. And then I think we're going to try backing up from that into a statement about eigenvalues. I'm hoping anyway. We'll see what happens.